Welcome to another episode of the Mapscaping Podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Jordan Walks. Jordan is the Director of Business Development at a startup called SpaceRake. And today on the podcast we're talking about using lasers to communicate between satellites, from the Earth to satellites, and from satellites back to Earth. But before we get into all that great stuff, Jordan puts all this in context. We walk through how we're doing it today, how we're using radios today, and what the difference between using radios and lasers might look like. Before we get started today, I want to thank Synergize for sponsoring this podcast episode. In fact, this episode is part of a mini-series of 3 episodes that Synergize has sponsored as part of the Copernicus data space ecosystem. So thank you very much, Synergize. I really appreciate your support. Hi Jordan, welcome to the podcast. So you are the Director of Business Development at a startup. I guess we could call you a startup called SpaceRake. Is that correct?
Yeah, absolutely. We're definitely a startup. We're spinning out of a university. It's been a lot of fun, and I'm really glad to be here to chat with you today.
Yeah, I appreciate you taking the time to come on. So the idea of this podcast episode is to talk about how Earth observation satellites get data back to Earth. And it might seem a little bit like trivial to some people, but it's actually incredibly fascinating. And I know that because I've talked with you previously. But before we dive into all of this great stuff, how we get data to and from satellites and maybe even data between satellites, maybe you could just give us a little bit of background about yourself. So at the moment, we know that you're Director of Business Development at SpaceRake. How did you get into this field? How did you get into satellite communications?
So I always knew that I wanted to work in aerospace. Never knew what specifically I wanted to do, but I was always pretty much just set on going and working in space. And so out of school, I had the opportunity to go work for a company called Ball Aerospace. They're best known for working on some of the big space telescopes for NASA, Hubble and James Webb, and things like that. So I worked with them for a number of years because they did a lot of really precise optical systems. They also did laser communications, and so that was an area of interest for Ball when I was there, and I learned the ropes from a lot of the folks over there. Been working in that field and a couple of others ever since.
Okay, so you've got a deep background in this space. Excuse the pun. But like I said earlier, the promise of this episode is to talk about that networking side, how we get data between satellites back to Earth and from Earth to satellites. So maybe we can start off with a look at how are we doing this today. So if a Earth observation satellite has collected an image over Earth, maybe you could just walk me through that process. What happens then? How does it get back to Earth?
Well, we're actually at a really exciting time where that's changing really rapidly. Historically, essentially, that data would be saved on the satellite. And then when that satellite passes over a ground station, a radio dish, you typically think of a satellite dish, it's usually actually a radio dish that's used to talk to satellites. But the satellite goes over the radio dish and it would download from the computer over a radio link, an RF link, down to the ground there. Depending on which era, that may have been stored on tapes, or nowadays they can connect directly to networks and just store on an Amazon S3 bucket, for instance. A lot of changes in the industry happening now, though, and people are automating a lot of the different steps in the process. You no longer necessarily need to have a human in the loop for typical day-to-day activities, downloading standard data, things of that nature. And they're also looking at doing what are called crosslinks, which is communicating from one satellite to the next. So you may want to have such a communication path if you want to talk to the ground very quickly, but there's no ground stations nearby. You can radio the information to a different satellite and it can go down. That's often done from low Earth orbit, which is a few 400 to 500 kilometers above the surface, all the way out to geostationary orbit, and then all the way back to the ground. So there's multiple different paths that can be used to get data down to the ground.
Okay, so just so I'm understanding this, either the satellite crosses or comes within line of sight, I guess we should say, of a downlink station, so a satellite dish, and it starts to download the data via radio signal, or it sounds like maybe there's almost a mesh network of satellites in space where if I need to talk to one quickly, they can talk between each other and either communicate to the satellite that's closest to a downlink station, maybe, and send it down that way. Or you mentioned something about sending it off to a geostationary satellite, I believe. Am I on the right path here?
Yeah, very much so. The mesh nets are actually pretty new. SpaceX is building a mesh net. The US government Space Development Agency, they're building a mesh net, and a couple other companies as well. But that's a much newer concept, and the larger numbers of satellites that are required to make that happen really weren't, it wasn't a doable thing until the launch price started to come down. So those concepts that make so much sense to us here on the ground, you may have a mesh net in your home for your Wi-Fi network. Those are actually pretty new in the aerospace domain.
That sounds something like that's more focused on communication as opposed to Earth observation.
Yeah, so the only real distinction there in my mind is the person who's doing the routing of the bits is what's in those bits. And so you may be communicating an internet signal like the SpaceX Starlink constellation does, or you may be communicating information from an orbiting telescope like planet satellites do. And so really the only distinction there is what's in the information you're transmitting.
Okay, yeah, that makes a lot of sense. Does that mean then that are we still waiting for that a satellite within that constellation to pass over or come within line of sight of a downlink station, or is it happening in a different way?
Well, in the case of a mesh net, there's so many new opportunities that come up with that kind of an architecture that's very exciting. You no longer need to wait for the satellite to pass over a ground station. In the industry would say make its next pass with relation to the ground station, because that mesh net, what you actually need is any satellite in that mesh net to be over a ground station. And so that's a big part of the value added by Starlink is that there's almost always, if not always, a satellite overhead that your internet transceiver on the ground can access and it can talk to. And then once you talk to that first satellite, you can route the signal anywhere in the mesh network, whether it's in space or on the ground. The same is very much true for remote sensing Earth observing satellites. Anywhere in the mesh net can talk down to the ground to a ground station. Then any satellite within that mesh net can then move data down to the ground.
And so far, we've been talking about like from satellite, from space to Earth. Is this also true from Earth to space?
Yeah, in principle, it doesn't actually really matter which direction. Of course, there's a lot of engineering details. How big is the dish? How much power can you put into the signal? But, to first order, in principle, it doesn't actually matter which direction the bits are moving. Oftentimes, links are bidirectional. In the case of Earth observation, remote sensing, typically you have more data coming from the satellite down to the ground, but that's not necessarily, there's no reason for that to be universally the case.
Yeah, I was thinking, you mentioned it before as well. I was thinking about tasking here.
Yeah, absolutely. So tasking requires an awful lot less data than the observing, side of the house does. So these satellites, you can task them when they're part of a mesh network. You can task them at any time. But traditionally, 10 years ago, and on many satellites today, the ones that aren't part of the mesh network, you can actually only send up tasking orders when that satellite's over a ground station, or you can use relay satellites such as TDRS, which is a NASA operated satellite that's much further out in low Earth orbit. And you can always talk to TDRS from the ground, and then TDRS is far enough away that it can see most of the satellites that are in Earth orbit much closer to the planet. So you have a couple of different ways to route tasking. Typically, you wouldn't want to route actual mission information, the data that's coming off of the instruments through TDRS, because there's just not a lot of bandwidth for that. But TDRS is used commonly for tasking and for getting telemetry down from the satellite.
And when you talk about TDRS, you're talking about I think you mentioned a geostationary satellite before. Is this the one?
Yeah, so geostationary and geosynchronous are two different flavors of essentially the same thing. And basically, what that means is the satellite is positioned in space so that it goes around the Earth once every 24 hours, about the same period for one day. So basically, it stays over the same spot at all times. But the way that the orbital mechanics works out, that's actually quite a ways from the Earth. So there are different constraints in using those satellites, and the limited bandwidth is one of them.
And just so I'm clear on this, up until now, we've been talking about radio communication. Is that correct?
That's correct. That's what's usually done today.
Yeah, and why is radio communication a good choice for this kind of communication between satellites and the ground?
Well, it's considerably easier to point and steer a radio beam than it is, some of the other options that are out there. Radio technology, it's well understood. It's been very well engineered, and you can move quite a bit of data through radios. But there are also some constraints that are causing people to look elsewhere.
This is a perfect segue onto what you're doing. Thank you very much for walking us through that. I really appreciate it. I hope it gives the listeners a good sort of context to work from when we move on and talk about another way of doing this. So my understanding is your startup is doing something interesting with networking satellites and laser communications.
Yeah, so our vision at Space Rake is that we want to see satellites become internet connected devices. And for that to actually be possible, there's a couple of different things that need to happen. from a user's perspective, they need to have more bandwidth, more data that you can move per second or per day, and you need to be able to do it continuously. And so that makes it a little bit hard when you think about the typical, the more traditional mission operations profile where you upload and download data every time the satellite passes over one of the ground stations. And the ground stations are spread out all over the planet, but it's a really big planet. And so that doesn't allow a continuous access to the satellite. So that really makes it hard to think for operators and designers of these missions to think about satellites like you would any typical internet connected device.
Okay, so I mean, I completely understand that, but what is the solution to this then?
Yeah, so the solution that we see, both for the needing to move more data and to be able to do it continuously, lies in the laser communication well. So rather than using radios to send data as we've been doing for many decades, both terrestrially and in space, we've started to use lasers. With lasers, you can move quite a bit more data through a very narrow beam. It's more like a pencil beam or a radio dish. A radio beam looks like a big cone, and by keeping the energy in that beam much more focused, we can, in a pretty energy efficient way, move a lot more data a lot faster using lasers.
It's the value proposition here that using lasers, I can use, you said a lot more data, a lot faster, but is it that I can move more data or can I move more data more often? I guess the constraint that you're working against here is that we can't move enough data the way it is today using radios into lasers. Okay, we can send bigger packets of data quicker down to the earth, or is the constraint we don't really need to send more data down to earth. We need to be able to do it more frequently or on demand.
So there's two constraints there. The lasers are very definitely a solution to the first one, moving more data. And then there's newer architectures that such as the mesh networks that we've talked about, that can use lasers to move a large amount of data and also do it in a way that allows continuous access to those satellites. So lasers aren't, there's no silver bullet, but they're a big part of a solution moving forward where satellites are going to need to be able to move a lot more data. And then the constellation architectures, where you have your satellites placed at what time, how many satellites there are, and how they work together, that's how you're going to start to get into the always on part of the problem.
But what does this mean for the ground station side of things? Like what are these receiving stations or disks or receiving places going to look like for lasers? Are they equally massive constructions like what we see today when we think about a downlink station, or are they smaller? Are they more mobile? Do we have more of them?
Yeah, so currently, most of them look essentially like the big professional grade astronomy telescopes. They have a building dedicated to them. They have a dome that can be used to cover the telescope when it's not in use. Oftentimes, they're on big pylons that go down into the ground to get a lot of stability. That's certainly a good way to be able to get a really big aperture so that you're not wasting any energy. You're collecting as many photons as possible, but it's pretty impractical for using those types of things in larger numbers. So recently, there's been some work on making these laser ground stations quite a bit smaller and portable, actually. So recently, out of MIT, which is some of the technology that we're working with, they've been able to demonstrate human portable ground stations that can be set up and used to communicate with satellites with using lasers, pretty much any location on Earth. So in the future, going forward, I would fully expect to see that in many circumstances, such as for the military or for disaster response or something of that nature, where you want to be able to temporarily set up a laser communication terminal, you're going to be able to start to do that. And it's going to be a telescope that's, about 10 or 15 inches across. So it's not small, but it's not particularly huge either.
We talked about this idea of these ground stations for lasers. They could be they're much smaller, much more portable. And we talked about the ability to move a lot more data via laser than what we can today through using radios. But is one of the advantages, do you think it could be we could move a lot more data and move it closer to the compute instead of putting it in Antarctica, for example, and then moving it to the compute? Or is this is that like that transport time between Antarctica and I don't know, and Google's cloud computing infrastructure is that trivial?
Oh, it's actually very much not trivial. So I did a systems architecture study for a radio telescope that was going to use a big dish down at Antarctica, and From a radio telescope's perspective, data is data, and it doesn't matter if it comes from an astronomical target or if it comes from a satellite. From the detectors to at first pass, data is data. But they're collecting enormous volumes of data, and on the radio telescope, which is currently a lot more than satellites are downlinking, but that's changing as more satellites go up and more powerful sensors go up. We actually found that as we were crunching the numbers, the most effective way to move big volumes of data from the base at McMurdo Station in Antarctica, it may have been Amundsen Scott, I think it was McMurdo, to the central correlator where all the big computers are going to be, and really just to get it to anywhere that's got cloud access at that time, a couple years ago, was a C-130. And so we would put the data on the hard drives, fill up the
Yeah.
C-130, and fly it back to the US. And so,
Right. Okay.
moving data to austere locations is something that's very much not trivial even today. We take it completely for granted in our really well connected, interconnected lives in these cities that we live in. But when you go out to austere, remote locations, satellites actually are going to become maybe the easiest way to move data. So if you have a laser system down at McMurdo, it may be that that's the best way to move data from your radio dish. So you collect the data with your radio dish, and then you blast it up to a satellite with your lasers because you can put more data, more bits per second on a laser than you can on a radio dish or on a radio link. So, ironically, that may actually be you may collect the data on the ground and then send it back up to a satellite to move it over to get down to the ground elsewhere.
Fascinating. Have you ever seen those maps of the communication cables that are running, connecting us all here in the world?
I'm maybe I have, but I can't think of what they might look like offhand. I would imagine a lot of links from North America to Europe and
Exactly. It looks like the subway maps.
Mhm.
It just spread across the whole world. Fascinating. But what's more fascinating is thinking about putting some of that infrastructure in space and moving data around the world like that. Why put a cable from North America to, Scotland and then over to Denmark, for example? Why not just beam it up into space and transport it that way?
in not the terribly distant future, I expect that's going to be the way a lot of things are done. And actually, there's some use cases today where even if you have an undersea fiber cable, it's still better to use satellites. For example, if you look at high frequency traders, right? Every millisecond counts when they're trying to, buy and sell, whether it's stocks or whatever it is they might be trading. And those folks are always looking for a way to be just a little bit faster than the next guy.
Yeah.
And it turns out when you run the math, because light moves faster in free space than it does in glass, the data can get from North America to Europe just a little bit faster if it goes through a satellite than if it goes through undersea fiber cables.
Wow.
And there's not a lot of instances where that time difference matters. But we have talked to high frequency traders that would be interested in that technology if it became available. And in that world, because it's all relative competition, they're really just trying to beat the next person. They don't care about being absolutely fast as they can be. They just care about being faster. But as soon as one of them adopts it, I would imagine pretty soon most high frequency traders that have any communications that have to go between the US and Europe in a timely fashion are going to be wanting to use satellite links.
Wow. So here on Earth, there's constraints around what frequencies you can broadcast on your radio signal. Is that also true in space?
Yeah, absolutely. So selecting your frequency that you're going to transmit on and getting permissions to use different frequencies is a really big problem that satellite operators run into all the time. Whether they're R&D payloads that NASA might be doing or their operational missions that commercial company might be trying to carry out, the actual selection of your radio frequencies, the amount of power you can transmit on that frequency, and when you're allowed to use that, that's a very challenging regulation driven problem, and that's something that's really starting to creep into the traditional radio satellite communications because it's getting harder and harder to find spectrum that you can allocate for your mission.
So this might be the world's stupidest question, but do lasers solve this problem?
Definitely not a stupid question at all. And they do solve that problem largely because when you think of a laser beam, if you think of a laser pen or something, the light that comes out of it is pointed and focused in such a narrow pattern that it doesn't interfere with other laser communication devices. You don't want to shine it directly down a telescope because you might fry the detector, but short of pointing it directly at somebody else's satellite or instrument, you're really not going to interfere with other communications that are going on. And that's very much different from using a radio. If you think back to when you were a kid and using walkie-talkies or toy handheld radios, you would talk to one another, and sometimes you might pick up, a little bit of the FM radio, from the local radio station, or you might pick up, your other friends around the neighborhood as they're talking on their sets, whether or not you want to hear those things. But that doesn't happen when you're using a laser because everything, the laser has to be pointed so precisely, and so do the detectors. They also have to be pointed very precisely that you essentially can just ignore all of the other communications that are going on.
I realize that it's not as trivial as I'm making it sound, but this would solve that problem. This would mean there's basically unlimited bandwidth now in terms of communication because we don't have those constraints around, oh, somebody owns that frequency or somebody's already using that. Or if I get too close to their frequency, I will create a lot of noise in their signal.
Yeah, that's really one of the big benefits to using lasers. You can typically move more data as well using a laser, but one of the really enticing things, especially for modern satellites, they've been able to design the satellites to only send as much data as you can transmit on a radio anyway. But using a laser, you don't have to worry about the spectrum allocation issues.
Oh. So you've used this analogy a couple of times now of the laser pen, the pointing pen with the extremely narrow beam. And I'm guessing there's some smart people working on the hard problem of hitting another satellite from a satellite and using that as a communication bridge. This sounds like an incredibly tough problem to solve.
It certainly is not trivial, and there's a lot of people working on it. It has been demonstrated, so we know it's doable, and there are a number of different groups that have done it in different capacities. One of the laboratories here in Massachusetts actually was able to communicate with a laser from, they set up their ground station in New Mexico, and they were able to communicate all the way out to the moon and back. And so one of my friends actually worked on that mission, and he's got a lot of great lessons learned from that. But it remains a very difficult problem, but it's certainly transitioned over the last number of years to be a difficult problem that has good solutions. And looking forward, that's essentially how people, both commercially and in the government side, are looking at it.
So in terms of Earth observation satellites, the optical satellites, the ones that are taking images of the Earth using passive sensors, they really struggle with cloud. Is this going to be true for a laser beam as well?
Absolutely. So that's one of the biggest pitfalls for using laser communication if you're trying to go from space down to the ground. And it's really just light doesn't go through clouds very well. And radio waves will attenuate, they will be dampened out to some extent as well. You may notice this if you have, say, satellite television. When it rains really, really hard, you might start to lose your signal quality. But it takes a lot more than just a typical cloud like you would have on a normal cloudy day to really dampen out the radio signal, even though that will have a really big impact or make on lasers or make it entirely impossible altogether.
Again, I feel like I'm asking a bunch of really naive questions today. But is it a question of just turning up the power on the laser? If we have a more powerful laser, can we better penetrate cloud, or is cloud less? Does it add less noise to the signal? Can we get through it easier if we just simply add more power?
To some extent, you can get more signal through, but really that's just not a practical solution. And once the clouds are there, they're going to scatter the light pretty much regardless of how much power you get there. Unless you want to create like a laser weapon, then you're going to be looking at so much power it'll kind of go through anything. But the goal is to communicate, not to be putting holes in things. So that that's kind of frowned upon to use a communication laser that's going to just burn its way through whatever. But yes, you can make a laser that's powerful enough that it'll go through a lot more than a typical communication laser would. But that's something that's going to be really unsafe for people's. Even the scattered light can cause harm to people's eyes if you make the lasers powerful. So you try to get by with as low a power of a laser as you can, so that if there is any light that gets scattered off of something, goes off the atmosphere, or bounces off of a mirror on the ground or something of that nature, it's not going to bother any body or any cameras or anything like that. So you really want to not be causing any harm with your system.
When I heard myself ask that question, I thought, Maybe I've seen too much Star Trek as a kid. Maybe that's where it came from." We talked a little bit about power there. Like, is lasers or radio? Is there any one of them that's the clear winner when we talk about efficiency? Because we have to have batteries on board these satellites. We have to solar panels on them to create the power to run all these things. And my guess is we want something that's incredibly efficient. Can you say anything about which one is more efficient, or are they just equally efficient in different ways?
That's definitely not a simple question. That's the kind of question that you need to take a holistic look at the mission, at the satellite, and at the ground stations to come to an answer on that. And so you can build up an engineering tool called a link budget to figure out how many watts per bit essentially you're going to need to transmit. But that's driven by a number of different things. One is how big is the radio dish, or how big is your telescope on the ground. The other one is how big is your radio dish or telescope on the satellite. How well can you point? So if you have a laser system and you can point really, really well versus just almost well enough, right? You actually have a big drop off in the amount of power that's received. But in general, as a rule of thumb, acknowledging that I might anger a few engineers that are listening to this, but in general, the beams that lasers generate are so much more narrow than radios that you're going to probably find yourself being a bit more power efficient using a laser. But there's a lot that goes into answering that question, and the real answer requires a lot of engineering to come to a conclusion.
Yeah. So when I think about this, I think things like, okay, so we're already using radios. They're tried, true, they're tried and tested. We have the infrastructure to accommodate them, and it's working today. Sure, it could be better, but it's working today. And then you show up with lasers, and say, okay, well, there's no issues with licensing, radio frequencies. The spectrum is basically wide open. We can point them more accurately. The ground stations are much smaller, and we can move more data faster. Is there any one clear winner here? Is this going to be one of those things where, oh, we're going to have radios and lasers on our satellites going forwards? Or do you think that the laser here is just the clear winner? And I realize, of course, you're involved in a startup, but it would be interesting to hear your opinion about this.
Yeah, I think there are certain use cases where the laser is the clear winner. When you really need to move a lot of data off of a satellite, then lasers are definitely a clear winner. So if you think about, like 8K video, just a typical, is it 24 frames per second or something, you're generating a gigabyte or a gigabyte and a half of data per second. That's considerably more than you can move with a typical, radio link. However, it's actually right in line with the specs that the Space Development Agency has put out and is starting to purchase equipment for and fly equipment to demonstrate for their spec. They're moving to about 2.5 gigabits a second over 5,000 kilometer link lengths. But the downside is, because the laser beam is so narrow, it's that little pencil beam as opposed to like a much broader cone. If you're misaligned when you start, it's a lot easier to communicate with a radio than it is with a laser. So if you have two satellites that are trying to talk to each other and they're not exactly sure where the other one is, you may know pretty decently, but you're not exactly sure. It's very much to your benefit to have even a small low powered radio, because they're pretty cheap and they can be really low power, just to send an initial, hey, I want to talk to you and here's my location kind of a signal to that other satellite. And then that allows you to start to initiate the communication. And then based on that information, you can get your lasers aligned and start communicating with optics. So there are absolutely use cases where laser beats RF, hands down, but there are also use cases, and it's certainly not only the really low power example I gave you, but there are going to be use cases where radios are just better. If you are trying to communicate with someone in the tropics and you don't want to go through all of the rigmarole of using a mesh network, and you don't want to use all of these technologies that people are working on today, you just really want to communicate directly from your low Earth orbit satellite to someone in a tropical region that tends to be pretty cloudy. Then if you don't have to move a terribly large amount of data, you are probably just going to decide a radio is the best way to go.
When do you think we're going to see the first test case? When do you think you're going to have your first successful satellite to satellite via laser communication event? When do you think we're going to see ground stations like this kind of infrastructure spread out, or people start to focus on this kind of infrastructure for what you're suggesting here? Like, I guess what I'm asking is, I mean, you're clearly involved in a startup that's interested in doing this. You can see potential in it. How far off are we from making this a reality, do you think? Because it seems to me that the space industry, although it moves very, very fast, it's still like we're still talking about massive investments, and people are going to take time. Like they've already got something that's working.
We're well past the point where demonstrations have already happened. NASA and other government organizations have demonstrated ground to the moon laser communications and satellite to satellite communications. So the technology has been developed. What is being developed currently and what's developing very quickly in the space domain is actually the business cases. And so I think we're going to see people say, well, as soon as as soon as the ability to move more data is available, I'm going to use it. But then we also have the other side of people saying, well, nobody's ever asked us for more data, so we're going to stick with our radios. And there are certain cases where maybe people don't want more data, but if you just think about the technology and how rapidly sensor technology advances, I mentioned a gigabyte or two, or a gigabit or two per second for 8K video that you can shoot on your iPhone. It seems awfully reasonable to expect that a satellite would be able to do as much as your iPhone. But in reality, it can't in many ways because it's limited in its communication. And so the magic of your iPhone actually is the fact that it's so well networked and so well communicated. And once satellites have the ability to tie into networks to the same degree that your iPhone or your Android can connect to the 5G network, then we're going to start seeing a lot of use cases that maybe people haven't thought of today because there's been so many constraints on the data that they can move. So a lot of the traditional uses for satellites, the science missions and things like that, you can design largely around, limited data bandwidth. But as we're building new business models, a lot of doors are being opened by having the ability to move more data.
Those are some really good points you come up with there. It's going to be, if we didn't have those constraints, it'd be interesting to know if people would still be so focused on the idea of edge computing, for example, because my understanding of that is that well, it's expensive to move, data back and forth between these satellites. And if your image is completely covered in cloud, for example, why not find out on the satellite and then not send that image? But if they didn't have that constraint, I guess they would just ship everything to the ground. Say, hey, check it out down there.
Well, I think what's probably going to happen, and this is my guess on this, reasonably educated guess, but we'll know in hindsight, is people are going to find a use for every bit of bandwidth that you can give them. Somebody's going to find a way to use it. And in parallel, at the same time, people are going to find a use for every bit of computing power that you can give them. So I don't think that edge computing and higher bandwidth communications are necessarily in competition with one another. I think they're actually going to combine to really build entirely new capabilities and use cases that have before now been unavailable to people.
Recently, I've seen some really interesting use cases for GPS signals, for example. People have been able to, based on the multipath reflections of GPS signals up into a receiver, over long periods of time, they can see how the ground cover is changing around these base stations. Have you seen anything or heard anything that might suggest that this might be more than just a way of communicating between, two different sensors? That this might also be a way of collecting data or making measurements?
Absolutely. So there are a number of different researchers that are looking at taking measurements, laser measurements and RF measurements to that point to measure atmospheric effects. So if you have two satellites that are spread out far enough that in order to view one another, they actually have to look through a little bit of the top of the atmosphere. If you send a laser from one satellite to the next, and you know the properties of that satellite, you can actually infer an awful lot about the atmosphere itself. So it seems reasonable that one might then be able to start to use communication paths. You'll see attenuation at one wavelength or frequency versus another one, and you can start to look at incidental, bits of scientific information, just like that GPS multipath bounce measurement is an incidental piece of information. But there's a lot of very smart people out there, and the more information and the more accessible you can make that information, I think the better.
This might be a little bit of a crazy side note here, but are you familiar with the Grace project, the Grace satellites?
Yeah, I'm actually quite familiar with them.
Huh. Isn't part of the magic that they are linked? So they're not just following each other closely, but they're linked together by some maybe lasers, maybe radios.
Absolutely, that's the entire basis for their measurements. So what GRACE is it's a pair of satellites, and the first one there's now been a second, the GRACE follow-on mission that was launched, I believe, fairly recently. But the first one was all radio based, and what it did is it took a radio wave and it transmitted it from satellite A out to satellite B, and then satellite B took that radio wave and in a very carefully controlled manner amplified and reflected it back to the first satellite. And what that allowed them to do was measure extremely precisely the distance between the two satellites. And then when the first satellite, both satellites were orbiting essentially exactly the same, except for they were separated out a little bit in their path. And so when the first satellite would go over a heavy object, take the Alps, for example, it would accelerate just a little bit to go faster than the second satellite. And that would cause the distance to change between them. They get further apart like two cars on the highway. And then when that second satellite caught up and it went over the Alps, it would accelerate and catch up a little bit to that first satellite. And so they're able to take that and measure the density of the gravity field of the Earth, and they can do a bunch of mathematical modeling to pull out, what is the density of the planet locally beneath those satellites. And then when they did Grace follow on, because it was a scientific mission first and foremost, not a tech demonstration mission, they maintained the original RF radio frequency capability, but they added an optical, a laser-based technology. And so they took that laser and very, very carefully stabilized the laser. And the first satellite sent it out to the second satellite. It received the light, amplified it in a very specific and careful fashion, and sent it back to the first satellite so then it could compare. And using the laser, they were able to greatly improve the accuracy of those measurements.
Wow. So I'm already thinking, let's do this, but like with a mesh network of a huge constellation of satellites and see what happens. Not only would it be incredible, like a communication device, a communication network, but it would be amazing to see the kind of data that would come off something like that over time.
And that's a really great example of the kinds of things that you can do when you start increasing the number of sensors. So the amount of precision that had to go into the Grace systems was actually pretty incredible. And it was, from a commercial perspective, wildly impractical. However, if you've got 10,000 satellites and they're all pretty good, maybe they're not as good as those two that NASA and JPL did, but they're all pretty good, then you can start pulling together a lot of information. And some of it is going to be the same, and some of it might actually be a little bit different than that original mission that they did. But you're going to be able to get a lot of good information, even though the satellites aren't quite as precisely made or engineered when compared to the original science class satellites.
Whew, wow, Jordan, we have covered a lot of ground. Thank you very much for bearing with some of my, relatively naive questions, but I really appreciate it. I feel like I've learned a ton. I hope other people listening to this have learned a lot as well. Can I ask you just one more question though, please?
Yeah, absolutely.
So this sounds amazing, right? And I know you've said time and time again that you've proven this. You've done experiments. You can shoot lasers to the moon and get it back again. You've created this like a ground station that a human can move around, for example. And we've got examples like the Grace project here. But when you tell people, do people push back and say, no, it's like this is not the way forward, or we're too early, or what do they say? Because my guess is that this is not for everyone. Not everyone's going to think this is a great idea. So when for those people that don't think it's a great idea, what do they say to you?
Yeah, so there's definitely detractors, but for the most part, people recognize the value of being able to move more data. And there's a really great analog on the ground. Think of how much capability has come just from the fact that you can move bits from your computer to your phone or your phone to your friend's phone. They see that, and the folks in the aerospace world, they want to make that possible for satellites. But where you tend to get a little bit of pushback is in the space domain, because once you launch a satellite, you can't, with very, very few exceptions, and Hubble, the Hubble Space Telescope was one of the exceptions, but you really can't get that satellite back and fix something that went wrong.
Yeah.
So that drives up the cost of every satellite, and it also drives down the risk tolerance. So most people really want to use hardware that has been already demonstrated. And so there's a big sort of reluctance to bring new and try new hardware in the space domain. And some people, especially that are at newer companies, SpaceX is a great example of moving fast, breaking things, learn from how they broke, fix it on the next one. That the paradigm is shifting. So there's an increasing appetite for things like laser comms, especially with some of the funding that's been coming out of the U.S. government and some of the demos that NASA and ESA have done. But when it comes down to actually, all right, well, let's plan to put one on your satellite, then people kind of say, whoa, it's great to have that on other people's satellites, but has it been tested? I don't know if I want it on my satellite if it hasn't been tested. So that mindset is changing, but it's definitely the case that people want to have really, really well vetted and well tested hardware before they put it on their satellite. And so that's probably the biggest pushback is, well, that's great. You guys have done a demo or two, and you've shown that you guys can pull this off, but you haven't flown 1,000 of these. You haven't done this 1,000 times. If you think about, you buy a Toyota Camry, they've made millions of them, and that's why they tend to work so well. But if you buy a hand-built bespoke car from some shop somewhere, there's a good chance that you're going to have to take it back to the shop to get some things tinkered on or tweaked. and you just can't do that on a satellite. So there's a little bit of a, not on my satellite. Are you going to be using your, early and developing hardware? That's probably the biggest pushback.
Yeah, and to be honest, I can understand that as well. Is there anybody that's starting to talk about standard, like a standard way of communicating? Yeah, obviously, we were talking about lasers, but I mean, a standard format, a standard, I don't know what you do with lasers, but some sort of standard around this, because I think you hit the nail on the head before you used the word bespoke. I can understand why people find that terrifying. But as soon as you start to say, this is standard, we use it here, here, and here, point to 3 different industries where we use it, and it works just fine. We have a standard way of communicating as well. This is interoperable. Put it on this satellite, you'll be able to talk to any other satellite. The standard will live on beyond us as a company, as a startup.
Yeah, interoperability is a huge word there. We're starting to very quickly get into the position where there are several standards that are starting to come out right now. NASA has a standard. The Space Development Agency, which is under the U.S. Space Force, they have a different standard, and they have slightly different ways of modulating, slightly different ways of encoding, slightly different ways of doing just about everything. And so it's helpful that there are standards to work towards. The jury's out yet on which is going to be the standard that ends up really taking over. But right now, we're kind of at the point, if you think to 15 years ago when every cell phone carrier had a different plug for their phone. And if you switch carriers or you switch phone models, you'd have to go buy all new cars, car plug and wall plugs and everything like that. We're kind of at that sort of a position with laser comm systems for satellites. If you want to talk to a satellite that's on the SDA, Space Development Agency specification, that's not necessarily going to talk to the NASA specification. It's not necessarily going to talk to the European Space Agency specification. DARPA has made a big push. There's a program to try to come up with laser communication terminals that will work with many or maybe all standards, but that actually increases complexity in a lot of different ways. And it may make that cost prohibitive or size prohibitive for smaller satellites. So I hope eventually, hopefully not in the too terribly distant future, everybody will coalesce around a single standard, but it doesn't seem to be the case yet.
Yeah, well, I think the same story is playing out in a lot of different areas of the geospatial world. So I'm not surprised. Let me say it like that. Jordan, thank you very much. Look, I've really enjoyed this conversation. You've definitely opened my eyes to what's possible and what the future might look like. And also, I really appreciate the context that you provided at the start, like the way we're doing things today. Yeah, fascinating. Thank you very much. We mentioned the name at the start, but maybe you could say it again for us now so people know where they can go to reach out to you to follow along with your startup and continue this conversation.
Yeah, you can find me on LinkedIn. Otherwise, my startup name is called Space Rake, SPACERAKE, and you can find us there on the internet.
Wonderful. Thanks again for your time. Really enjoyed it. Cheers.
Thank you very much. Take care.
I really hope you enjoyed that episode with Jordan Walks. I'll put links to his LinkedIn profile and to his startup Space Rake in the show notes so you can check it out if you would like to. So I personally really enjoyed this episode. Really interesting hearing about how satellites communicate today, how we communicate with satellites today, and of course what this might look like in the future when we move maybe from radio or when we move to the possibilities of communicating via laser, so optical communication. But I think perhaps what's more fascinating here is the little thought experiment. So what happens if our satellites become internet devices, part of the Internet of Things? What if they were always on, always connected in the same way that your phone is, always on and always connected? What will people do with that? What will that enable? And I guess the really easy answer to that was just more. It'll enable a lot more of all of the things that we're doing today. But perhaps the more interesting answer will be like, yeah, but what about those things we're not doing today? What about those things that are not possible today? I can't see the future. But I think this is going to be something really interesting to follow along and see how it develops. So I mentioned in the introduction that this episode is sponsored by Synergize as part of Copernicus data science ecosystem. And this is not the first episode they've sponsored. They've sponsored 2 others. I'll put links to those in the show notes because I think that if you like this, you'll also like those ones. I'm sure of that. There'll also be links to other relevant episodes in the show notes today. And I think probably the one that deserves special mention here is an episode around how to keep your satellite pointing at Earth. But again, all of this will be in the show notes, so check it out if you're interested. That's it for me. That's it for this week's episode. Thank you very much for tuning in all the way to the end. It's greatly appreciated. I'll be back again next week. I hope that you'll take the time to join me then. Bye.